Hello and good day, everyone. So we're now down to the last topic for beam design, which is design of reinforced concrete beam. So I made a two-separate lecture for this. So first is this lecture in which I will discuss to you what is a reinforced concrete beam and the basic design consideration. And the next lecture, I will discuss the steps on how to design the reinforced concrete beam. So I will show you the formula uh, together with an example so that we can understand how to design it. Okay, but first let's discuss the basic information of what is a reinforced concrete beam and its design consideration. Okay, so let's start. So first is we define reinforced concrete beam. So reinforced concrete is a composite material consisting of steel reinforcing bars embedded in a concrete. So unlike timber, in which there are only one material being used, so reinforced concrete beam is different because it utilizes two materials. So it's steel reinforcing bars and a concrete. So because of this, we need to have separate another principle on how to design this because of there are two materials being used. So concrete has high compressive strength but low tensile strength. Okay, so remember that statement, no? Because as we go through, or I think in the next slide, we will use or we will compare that statement. Okay. So steel bars can resist high tensile stresses, but will buckle when subjected to comparatively low compressive stress. So the statement a while ago about concrete is different with steel bars because they're opposites. So if steel bar can resist high tensile, concrete will not. But concrete can resist high compressive stress, but steel bars will not. Okay, so they're opposite. So that's why to utilize their property, this property, we need to combine this. So proper zoning is important in this part. So steel bars are used in zones within a concrete member which will be subjected to tensile stresses. So as you recall, as we derive the flexural formula, with the beam bend, this part here it will be subjected to compression, and then this part here is subjected to tensile. So that's it. You know the property, so that's why we need to place this reinforced bar in this part, in this region, because it can resist high tensile. Okay, so proper zoning is important with this. So reinforced concrete is an economical structural material which is both strong in compression and bending. That's because of the property of both material being used, the steel bars and the concrete. So concrete provides corrosion protection and fire resistance to steel bars because steel bars are located or embedded in the concrete. It is being protected by the corrosion and fire because it is located inside the concrete. Okay, so I think that's a very common definition, basic definition of what is a reinforced concrete beam. So now let's go to the design consideration. There are five design consideration, but I think there are a lot of consideration. But I think this is the most common. So first is the beam proportion, deflection, estimated beam weight, selection of bars, and the last one is cover. So I think the sixth design consideration is the spacing of bars. But we will discuss it later on in the discussion about uh, construction materials. Okay. So for now, let's discuss here. Let's discuss these five, and let's start with this beam proportion. So unless architectural or other requirements dictate the proportion of reinforced concrete beam, the most economical beam section are usually obtained for shorter beams. So the same with uh, timber design. As much as possible, we need a shorter beam. No? If we can design it shorter, it's better, because the longer it beam, if it is simply supported, it will basically sag or deflect, which is not good for the structure. So up to 20 feet or 25 feet in length. So when a ratio of dB is in range of 1.5 to 2. So that's very common, no? 1.5 to 2 na ratio for the depth and the width. Okay, for largest span, if it is not difficult to avoid, better economy is usually obtained in depth narrow section are used. So the depth may be as large as 3 or 4 times the width. So I think more siya slabs siya nga, instead nga nakaana is nakaana siya. Okay, so mo siya ang common if longer span siya. Okay, however, today's reinforced concrete designer is often confronted with the need to keep members rather shallow to reduce floor heights. As a result, wider and shallower beams are used more frequently than in the past. So furthermore, beam widths are often selected in multiples of 2-inch or 3-inch. That's why you hear beam, what is the size of the beam? 2 by 2, 4 by 4. So we have 6 by 6. So that's the multiples for, common multiple for beam widths. So the next one is the deflection. So for simply supported slabs, normal weight concrete and grade 60 steel, the minimum depth given the deflection are not computed equals to L over 20, where L is the span of the slab. Okay, so for calculating the deflection, I think the same with calculating the deflection of homogeneous beam. So we have an established deflection for simple supported, cantilever, continuous. So you can use that formula. You can use the formula again for this type of beam. So the minimum thickness provided apply only to members that are not supporting or attached to partition or other construction likely to be damaged by large deflection. So let's move to beam weight. The weight of the beam to be selected must be included in the calculation of the bending moment to be resisted, because the beam must support itself as well as the external loads. Okay, that's a very common statement, no, in designing. So in designing of beam, we need to include the weight of the material, which is basically a type of dead load, and also the external load. So that's the very common statement for beam design. So we need to, so in estimating the beam weight, what we need is the cross section, because if we multiply the cross section of our beam into its density, we can convert it into a uniformly distributed load. So from that, we can calculate the reaction or the maximum bending moment, the maximum bending shear, plus we add the external load, then we can design the beam. So the issue here is how to design or how to estimate the cross-section of your beam. So we have here this table. So it's promote the minimum thickness of your beam and solid one-way slabs. So just be familiar with the table. So L is the span in inch. So you have this formula here. So for simple supported, for one end continuous, both end continuous, then cantilever. So all this part here is a type of beam. So they have a respective how to calculate the minimum thickness. So we have here the notation for that one. So we will try to show you, I will try to show you how to use this formula here in order for you to understand it in our next session. Okay. So another practical method for estimating beam size is to assume a minimum overwall depth H is equal to the minimum depth. Then the beam width can be roughly estimated equal to about 1/2 of the assumed value of H. And the weight of this estimated beam calculated is just equal to BH over 144 times the concrete weight per cubic foot. Again, so that's kind of, so that's why we need to calculate, we need to design the cross section in order to calculate the weight of the beam. So remember, just remember that the approximate weight of the concrete is 150 pounds per cubic feet if the weight of the steel is included. So since we're talking about reinforced concrete beam, so we need to include the weight of the steel bar. So after mu is calculated, mu again, this mu is the load, the live load, the dead load. Again, so if you recall the structural loads, I have the I presented there lots of formula about mu. So what will happen if the present is live load and dead load? If there is a wind, or rain, so that U, actually it's gonna U dapat to siya. So after U, mu is determined for all of the loads, including the estimated beam weight, the section is selected. Okay, so if the dimension of this section are significantly different from those initial assumed, it will be necessary to recalculate the weight and mu and repeat the beam selection. So you need to compare. You need to compare your estimated, and also the design calculation. So again, so we need to estimate. After that, we will compare that in your calculation. If it is quite different, we need to recalculate. So after required reinforcing is, okay, no, the next one is the selection of bars. So after the weight, the deflection, and the beam proportion, so the next one is the selection of bars. So it's really important, no, to select the proper bars. So after the required reinforcing area is calculated, Appendix A, I'm really confused what book is this, but I will try to find the book. So table A.4 is used to select the bars that's provided the necessary area. So for the usual situation, bars of size number 11 and smaller are practical. So it is usually convenient to use bars of one size only in a beam, although occasionally two sizes will be used. Bars for compression steels and stir-ups are usually a different size. Okay, so stir-ups, I will discuss what is a stir-ups is later on. Compression steel is the upper part, the tension steel bar are the bottom. Okay, so this is the table. So you have here the number of bars, the number. But here I will show you in our next video how to use this table. Okay, the last one is the reinforced concrete. The reinforcing of concrete members must be protected from the surrounding environment. So this is covered. That is fire and corrosion protection need to be provided. The reinforcing is located at certain minimum distance from the surface of the concrete so that a protective layer of concrete called cover is provided. Okay, so that's why if you're familiar with I think kakita na gud mo mga examples sa beam that the steel bars are located inside. So there are certain distance before the surface of the concrete. You saw a specific distance before the beam. So that certain distance is what we call the cover. So in addition, the cover improves the bond between the concrete and the steel. So here is the example or the illustration. So we have here, this is the steel bar. This bar located outside is what we call the stirrups. So if you're familiar, if you saw in the construction, when they construct their beam, you saw a bar around it, which is basically being embedded. So that's what we call stirrups. So I think you're familiar with stirrups. Makita ninyo between sa beam niya na mga box. But usually in the Philippines, we commonly use this type of we did not commonly use this type We usually use the square one. So we have here the standard for the cover for a van. So the minimum cover required for concrete cast against earth is, as in footing, is 3 inch, and for concrete not cast against earth but later exposed to it by backfill. So precast and blister concrete or other concrete cast under plant condition requires this cover. So if your beam are located in the most suitable condition, most suitable environment, so you can construct your beam and with less cover. So first, placed in the compression side of this beam to provide support for the stirrups and to hold the stirrup in position. I think ours is not commonly used in the Philippines because we normally use stirrups, which is square one, not this type. We did not use this type of hangers. No, I don't know, but my experience, based on my experience, commonly we use stirrup that is square, so there, it is being surrounded, being attached around this compression steel bars and this is tension steel bars. So here is the tension, high compression. This is the tension steel bars. Okay, so I think that's all for the basic design consideration. So we will discuss the other uh, design consideration in our topic for construction materials. So in our next topic, we will discuss about the procedure and how to design this base reinforced concrete beam. So we'll show you the formula and also some examples for you to understand. So that's it, and thank you.